Let's go ahead and talk through the solution to this problem. So we're given this set A, which is the set of numbers of the form 1 minus 1 over n, where n is a natural number. And what we want to try to do is figure out what the supremum of this set is. So just to kind of think about the set, right, I'm going to have when n equals 1, I get 0. When n equals 2, I get 1 minus a half, which is a half. N equals 3, 1 minus a third, which is 2/3. N is 4, 1 minus a quarter, which is 3/4, and so forth. So if we think about this set, we can see it's getting bigger and bigger, but I'm going to only get up towards 1. So we can guess that the supremum is going to be 1. Then to show that, I have to show two different things. So we're going to use this sort of supremum analytically theorem. So first, I want to show 1 is an upper bound. And then second, I want to show anything less than 1 is not a lower bound. So for every epsilon greater than 0, if I take 1 minus that epsilon, it's not an upper bound, which means there has to be something in the set. So let's move this over a little bit. There exists something in the set which is bigger than 1 minus epsilon. So those are the two things I need to do to show that the supremum is actually going to be 1. So first, let's go ahead and just think about what I need to show that 1 is an upper bound. I need to show that 1 minus 1 over n is always going to be less than or equal to 1 for every n. And so again, I'm in my background work stage here. I'm just sort of thinking about what I want to show, and then I'm going to work backwards. So that's the same as showing negative 1 over n, subtracting 1 from both sides is just going to be less than or equal to 0, and that makes sense. N is positive. So that's just the same as showing, for example, 1 over n is greater than 0, which is the same as showing that n is greater than 0. And we do have that n is strictly greater than 0, so we'll actually get a strict inequality here instead of a less than or equals, but that's fine. It still gives us that 1 is an upper bound. So this sort of gives me an idea of what I need to do in the proof, even though when I write the proof, I'm going to not start with the thing I'm trying to show. Instead, I'm going to start with something that I know is true, and I'm going to work my way backwards. So that's what we'll see down below in the proof area. Okay, so now let's think about the background work for the next part here. Again, I'm trying to show for every epsilon greater than 0, there exists some x, I wrote here in x, but I meant in a, where that x is bigger than 1 minus epsilon. So if I think about all of my different x's in a, I'm going to get closer and closer to the supremum value of 1. But if I take something a tiny bit less than 1, I should be able to find something in the set bigger than that 1 minus epsilon. Because if not, then 1 minus epsilon would be bigger than everything in the set, which means 1 minus epsilon would be an upper bound, which contradicts the fact that 1 is the least upper bound. So that's kind of the ideas that we have. All right, so let's do it. I want to show, again, I'm just doing my background work so I can just work with what I want to show. I want to show there's some x which is bigger than 1 minus epsilon. Well, I know x looks like 1 minus 1 over n, and so I need that to be bigger than 1 minus epsilon. And so I'm just trying to figure out what the x should be. X depends on n, so I just need to figure out what the n should be. Let's see if we can sort of solve this inequality for what n should be. Again, I can subtract 1 from both sides. I can negate everything, switches the inequality sign. And so then switching everything around, I just need that n is bigger than 1 over epsilon. So if we're thinking about this, epsilon is a really small number, so 1 over epsilon is really big. So I just need to pick some n, which is bigger than 1 over epsilon. And I can usually think about that using the unboundedness property of n, or I can use an Archimedean principle. Okay, so that tells us here sort of what our starting points that we know should be. We know we can find this n. We know that n is greater than 0, and then we're going to kind of unwind those to get back to the things we want to show. So let's start the proof. So I'm going to say, right, I'm going to kind of give an outline here. So to show that the supremum of A equals 1, we will show first that 1 is an upper bound, and maybe I shouldn't have had a period here. It's not in that sentence quite yet. that 2, I'm just going to use shorthand here because it's a timed assignment. So for every epsilon greater than 0, there exists some element in the set such that that element is bigger than what minus epsilon. And that's going to what shows it's at the least upper bound, because anything less than 1 is not an upper bound because there's something in the set, right? So I'm just sort of telling the reader the things I'm going to show, and then we'll know that the theorem that we have, the Supremum analytically theorem, tells us that kind of gives us everything we need. Okay, so now I can say for 1, to show the first thing, I'm going to start with that thing I know, so I can say note that n is greater than 0. That's just for this n coming from here. So, like maybe you can say, watch n when n is a natural number. So, 1 over n is greater than 0. I'm going backwards along my steps. So, negative 1 over n is less than or equal to 0. I could have just strictly less than. It's fine. I just kind of threw in a 0 equal to at this point. Maybe I'll keep that strictly less than. So 1 minus 1 over n is less than 1. And maybe I can add a little note, adding 1 to both sides, so the reader knows exactly how I did that last little step because it was kind of unclear. This means if x is in A, x equals 1 minus 1 over n, so x is strictly less than 1. Thus, 1 is an upper bound. So we've shown that 1 is bigger than everything in the set. Okay, and now we do the second part. So for 2, I need to show for every epsilon greater than 0, there exists an x. So whenever we need to do that, we're going to fix this epsilon greater than 0 to be a fixed but arbitrary element. I usually say let epsilon greater than 0. You can say fix epsilon greater than 0. There's a couple different word choices you can use. And then I need to show there exists an x. So I actually need to give a formula for that x. So I'm going to say pick some n that's bigger than 1 minus epsilon. I fixed my epsilon, so I can calculate 1 minus epsilon, and I can then find an n bigger than 1 minus epsilon. And maybe I should specifically say that that n is going to be a natural number where it's bigger than 1 minus epsilon, which we can do by the Archimedean principle or the unboundedness of n. It's sort of one of these things that we're going to kind of use without saying why. We're just going to go ahead and say that we can do that. So then I'm going to, again, go backwards through my steps here to show that I wanted to do what I wanted to do. So we can maybe make it explicitly clear what x is. So letting x equal 1 minus 1 over n, we see that n is greater than 1 minus 1 over epsilon. So 1 over n is less than epsilon. So negative 1 over n is less than negative epsilon. So 1 minus 1 over n is less than 1 minus epsilon. Or x is less than 1 minus epsilon. Oh no, I went the wrong way. What did I do? Oh, sorry. Here we go. This one should have been a greater than, because I multiplied both sides by negative 1. And so that's a greater than, and so that's a greater than. Perfect. That's what we wanted to show as needed. Thus, we've shown anything, and maybe now we'll just really put this last piece in here about least upper bounds, less than 1, any of those 1 minus epsilons, is not an upper bound. Thus, 1 is the least upper bound. Right? I.e., that is to say that the supremum of A is equal to 1, which is what we wanted. Okay, so hopefully going through this, sort of showing that background thinking, showing how to write out these proofs, where we're sort of starting with some kind of weird statement, right? I'm just starting here with an n greater than 0, and I'm starting here with a n greater than 1 minus epsilon, 1 over epsilon. It might be kind of strange why we're starting with that, but that's coming from this background work. And we'll see a lot of this sort of style of proof as we move forward in the class.